Can you hear me?
Yes, sir.
Okay. Okay. So let's start. Uh, so we were discussing about radiation from accelerated point charge, and in the last, I think 2 or 3 classes, we are particularly focused on this. We are discussing about radiation that will be produced by point charge when it is accelerated point charge, when it is moving with a non-relativistic velocity or relativistic velocity. So we have discussed about the Larmor formula and also Leonard formula. So I will just briefly mention about these two formula and then gradually proceed. So let us first write down. So we are discussing about radiation from accelerated point charge. And we have learned about the Larmor formula. Larmor formula is about the power radiated by an accelerated point charge at low velocity. That is when beta is much less than 1. That is v by c is much less than 1. And in that case, the Poynting vector is r is given by r cap. R cap, I hope you all of you remember what is r cap. R cap, q is the charge, a is the acceleration, and divided by 4 pi c cube, and we have a dependence on theta like sine square theta divided by r square. So all of you remember this pattern that we discussed about this. So if acceleration is along this direction, then the radiation that will be emitted by the accelerated point charge will be confined in a direction which is perpendicular to the direction of acceleration. So it is a, and I also told you that this is a cross-sectional view of the radiation pattern. If you go to 3 dimension, you will see a donut pattern. So it is a cross section, and r is basically this r cap is any arbitrary direction r cap, which is making an angle theta with this. So sine theta, when I say sine theta, defined in this way. And if we integrate this over the entire spherical surface around this radiating point charge, then the power radiated by the point charge P total came out to be 1 over 4 pi epsilon 0, if you write in this way, into twice q square a square by thrice cq. This is the Larmor formula. And then we discussed about the Leonard formula. Leonard formula, which is actually applicable for actually any beta, because it is not limited to only relativistic regime. It is applicable for any beta, for any velocity, uh, any beta. And for this, we have not yet calculated the radiation pattern, but what we have done in the last class, that we uh, found out a relativistic generalization of this formula, which you call Leonard formula, by finding a Lorentz invariant. And then we have shown that the power radiated for uh, an accelerated point charge moving with arbitrary velocity can be written as twice q square and then gamma to the power 6 3. See, this was from the last class. This is from the last class. Beta dot square minus, we have something like yeah, you can also write mod beta cross beta dot square. So this was the power emitted. And clearly you can see when beta is much less than 1, then this formula reduces to the Larmor formula, right? And also we discussed two separate cases, that is when beta and beta dot are parallel. Case number 1 was when beta was parallel to beta dot, then what we get is basically the power radiated will be how much, this same expression as the Larmor formula, multiplied by, because when they're parallel, this cross product will be 0, right? So what you are left with, beta dot square is basically acceleration square by c square. So we have a 3c cube here, a square here, and the gamma to the power 6. So you have to multiply the Larmor formula by gamma to the power 6. And when beta is perpendicular to the acceleration vector beta dot, then clearly you can have cross product sine 0, sine 90 degree 1. So you can take beta dot square outside. So 1 minus beta square is 1 by gamma square, 1 by gamma square, and then gamma to the power 6 here. So we have gamma to the power 4. So the same Larmor formula multiplied by s q square a square by 3c cube multiplied by gamma to the power 4. And I also talked about, if you write down this expression in terms of force, not acceleration, then of course we can show that the power radiated in the perpendicular case will be more than the parallel case. Fine. So these are the Leonard and Larmor formula. Now, what should be our next goal? We want to understand what the radiation pattern would look like in case of relativistic motion, when the charged particle is accelerated with relativistic velocity. How should we how can we infer about the radiation distribution of the radiation around the charged particle? So that is our next goal. Okay, so let's start. So what we want to, okay, let me draw a picture here, so that will be, I think, convenient. So this is the coordinate system that we have considered. The charged particle is moving along some arbitrary trajectory. Okay, and say let us take this to be a field point, some field point which we label with a coordinate r, and we have some position of the point charge, moving point charge, labeled by say r prime, and this is curly r, right? So you can imagine a sphere of radius r around this point charge, and the radiation emitted by the point charge at any particular instant. We already know that the radiation which is received at the field point at time t was emitted at some earlier time tr, which is tr equal to t minus r by c. So the radiation which is emitted by the point charge will cross through a sphere of radius r. If you consider a field point here at a location r. So now if I know the Poynting vector, so what is the Poynting vector? SR. But remember, this SR is the Poynting vector which is expressing the amount of energy per unit time per unit area emitted by the accelerated point charge at the instant tr equal to t minus r by c. That is the energy which was emitted at retarded time tr and which is crossing through the and a spherical surface which passes through the field point, right? So if I write say sr dot r cap, what is that? Sr dot r cap. So sr is at a retarded time tr. The energy was emitted at retarded time tr. So that's why I'm writing retarded. It is just a notation. Just to remind you that the energy was emitted at retarded time tr, which is t minus r by c. So we already know about the expression. So what is SR? Maybe I should write down in the next page. Maybe I can also write it here if you can. I don't know how much space we have. Can we write it? Maybe we can go to the next page. So we want to calculate this quantity, and there is it has a physical meaning. What is the physical meaning of it? Okay, I should write it here. This is energy per unit time per unit area detected at the field point at time t. Dot product, I mean, that makes it scalar. So I'm talking about energy per unit time per unit area detected at the field point at time t, which was emitted, which was emitted by the point charge at time tr equal to t minus r by c. So I mean, the reason why I'm writing this, of course, you know the meaning of Poynting vector, so I don't need to explain what is Poynting vector. But the reason why I am emphasizing that there are two time involved in this. One is the retarded time, that is the time associated with the moving point charge, and the time, I mean, which is basically the time measured by the observer at the field point. Okay, so to just elaborate that point, I am writing this separately, that is r dot r cap is basically energy per unit area per unit time detected by an observer located at the field point and measured at time small t, and this energy was emitted by the moving point charge at some earlier time t minus r by c, right? So this is the physical meaning of this one. Now we already know the what is the Poynting vector, because Poynting vector, if you know the electric field, of course we can write down, as someone was asking me, that if I want to write down the Leonard formula without going to such relativistic generalization, can I just get E cross B? I told in the last class, yes, you can do it. So in this particular case, what I'm going to do, I'm just exactly going to do that. So I will just pick up the general formula for electric field and use that to calculate the Poynting vector. So let us see what it shows. So what was the expression for electric field for an arbitrarily moving arbitrarily moving point charge? So I'm writing that the electric field, the radiation part only. I am not writing the velocity part. Okay, ERT is equal to Q over 4 pi epsilon 0 C into R cross R minus R beta cross beta dot and then R dot beta dot whole cube. You can also a little bit simplify this, because if I take a r outside and divide it, it will become r cap. So let me write it that way. It will make it a bit simpler. 4 pi epsilon 0 c. So this is the radiation field, radiation component of the electric field. C, I have taken r outside and divided this. So this becomes r cap. Yeah, r cap cross, if I take another r outside here, so I think, yeah, this is r 1 minus r cap, yeah, 4 pi epsilon 0 r cap into, this will become r cap minus beta cross beta dot divided by, okay, this will become r, yeah, 1 minus r cap dot beta whole cube. So this is the electric field. And we already know that how to calculate the magnetic field if electric field is known. So magnetic field is simply 1 over C, because they are orthogonal, we can write them to be r cap cross ER. ERRT, of course, yeah. And what is the Poynting vector? The Poynting vector SR is 1 over mu 0 ER cross DR, right? So I will answer your question, because the question that you asked, that if we do not go for a relativistic generalization, if we suppose stick to this expression of electric field and then take an E cross B, what shall we get? Of course, we shall get the Poynting vector, and I will show you that this Poynting vector will give you the same formula, exactly same formula as the Leonard formula. Okay, so then I think then you will get satisfied. So SR equal to 1 over mu 0 ER cross BR, and I'm not repeating the calculation once again because ER and R cap are orthogonal, so you can take a because sorry, yeah, ER yeah, BR equal to R cross ER, so you can take a cross product of ER cross R cap cross ER and then drop one term to be 0 because R cap and ER are orthogonal, and that gives you this to be 1 over mu 0 C, C coming from this BR, and ER square R cap. Okay. So now let us go back to the point that I was mentioning in the last previous page, that we want to calculate this quantity. Which quantity? This one, SR, because our goal is to calculate the energy or power radiated per, yeah, okay, energy radiated during the some time interval. So we will assess that SR dot R cap. This was the quantity that I talked about in the last page. And now you see all we have an expression for SR. So what is SR dot R cap? This is 1 over mu 0 C. So let us write down that. Yes, you can simplify this mu 1 by ER square. ER square means square of this and square of this whole thing, right? So maybe I should write down it here. So if you simplify this, I mean just simply square this. So you will get 1 over 4 pi epsilon 0 square by 4 pi C. You see 1 mu and epsilon naught are related. So 1 by mu naught epsilon naught is C square. So I have just taken into account that in here. 1 by 4 pi epsilon 0, I am keeping them, keeping it always separate from the entire formula. It is up to you if you can mix them up. But I am doing this for the sake of this conversion from one unit to the other unit. And Q square by 4 pi C. There is 1 over R here. So it will be R square, 1 by R square. And then because we are squaring it, so that will be scalar quantity because the direction is taken into account into this R cap. So scalar quantity. So I have to take the mod of that, because if I take a cross product of 3 vector, of course that will be a vector. So I am just taking a amplitude of that. So that will be how much of that? R cap cross R cap minus beta cross. Sorry, it is beta. I'm sorry. This is beta, not beta dot. Beta cross beta dot. This is beta dot. Okay, this is beta dot divided by this R square is taken outside. So I am writing 1 minus R cap dot beta whole cube, and then square of that whole square, because ER square, you see this is ER square. So I'm just squaring this whole thing, square, and I'm putting a third bracket here and write this. You can write this or not. Do not. You cannot write this, but it's up to you. You may not write this. Retarded means, I mean, this is the energy which was emitted at the retarded time TR, not at time T. And now let us now calculate something. So which is the energy. So now we want to calculate energy radiated during a finite time interval or finite periods. Okay, finite period of acceleration. So suppose the particle is accelerating, and for a brief period of time, say from acceleration, say from TR equal to capital T1 to say capital T2. This is a brief, say interval of time, maybe delta T. Okay, T1 to T2, and within that time interval, how much energy is radiated by the accelerated point charge, that we want to calculate. Now, so how to calculate that? Because you already know the energy radiated per unit area, per unit time. So it just have to do an integral, because we have a time interval T1 to T2, and this is per unit time. So we have to integrate. So the energy radiated in this time interval will be E equal to, what is that? Is R dot R cap, this quantity which we have calculated here at a retarded time and over some time interval dt. Okay, Now you see this T and TR is you have to be careful about that. This dt is the time. This dt is the time interval measured by an observer at the field point. Okay, and in order to do the integral from the observer's perspective, we have to integrate according to observer's time, because tr equal to t minus what is that, r by c, right? So the time limit should be t equal to tr. What is the tr? Lower limit is t1, so this should be t1 and then plus r by c, plus r t1 at time capital T1. Where was the particle? Suppose this is r t1. That's, I'm not writing r1. Rather than writing r1 and r2, I am writing curly r as a function of t1. Okay, because the time interval is very brief, so it is not going to change drastically. This one, r by c, and the upper limit will be similarly. The retarded time is capital T2. Upper limit is T2. So T2 plus curly r at time T2 by c. So this time is observer's time. Now, if I want to write down the same integral in terms of the time of the moving point charge, the same expression can be written as equal to integral. You see the time, now the time interval should be the retarded time t1 to t2. So I write t1 t to t2. But if I want to write the limits t1 to t2, then I have to adjust here is r dot r cap retarded into dt. So I'm just introducing tr in this expression. The same expression here I'm writing dt, dtr and dtr here. So what is the essential difference? It is the same energy. Energy is not going to change, because whatever energy is emitted by the accelerated point charge will pass through that radius of that sphere of radius r. So this energy is same. The only thing that we are writing it, only difference between these two expressions is one expression is written in terms of the time of the observer at the field point, another in terms of the time of the moving point charge. So the physical meaning remains same. So look at this expression is r dot r into dt and dtr. So what is this? What is the difference between this and this? So this thing actually, see, energy per unit time is power, right? So this quantity is power radiated per unit area in charge on time. This is in the observer's time dt. T is observer time, and this is the charge time. So this dt dtr factor, when I multiply with this sr dot r cap, this was the reason I introduced this discussion. Sr dot r cap is already, and you have discussed this energy per unit time per unit area detected at the field point at time t, which was emitted by the point charge at time tr equal to t minus r by c. And if you multiply it with dt over dtr, this is basically the power radiated per unit area in the charge time. So there is two time involved here. One is charge time, one is the time in the charge frame, another is the time in the observer frame. So now, so we want to, what is our goal? We want to actually calculate the radiation pattern. What is the radiation pattern? That is whether there is any angular dependence. Like in case of a non-relativistic point charge, we saw that the radiation pattern depends on the angle as sine square theta divided by r square. So we got a I think it's a donut kind of pattern, and we want to know that in case of a relativistic motion, what should be the radiation pattern. So our goal is to calculate the power per unit solid angle. Okay, right? So solid angle, I know the entire solid angle is 4 pi. If we look at, if we take the all possible directions, 4 pi, and we want to know in which direction how much power is emitted, right? So actually what we want to calculate is dp d omega. power radiated per unit solid angle, right? This is this expression is giving you the power radiated per unit area. This is giving you the power radiated per unit area, and you want to calculate power radiated per unit solid angle. So this is power radiated per unit area. So what is the surface area of a sphere? 4 pi r square. So if I multiply this power radiated per unit area with the area of the sphere across which the power is passing through, we will get the total power radiated across all the solid angle. And if you divide by the solid angle, you get power radiated per unit solid angle. But you have to remember there is another factor here, dt dtr, which should be multiplied with that expression. And what is dt dtr? We have already calculated in this quantity in our previous discussion. But again, I may reintroduce it because you may have forgotten this. So what is r? If I remember, what is r? R is c times t minus tr. And just I can write this r square to be equal to r dot r, which is again c square, c square into t minus tr whole square. So if I take a derivative on the left hand side and right hand side, what do we get? I get twice, because there are two terms. First take a derivative of this one, keeping this intact, and then again repeat this. We'll get twice r dot del r del t equal to twice c square t minus tr, and then take a derivative of this quantity. So we write 1 minus del tr del t, right? Again, if you remember, the del r del t is what? We just calculate del r del t, del r del t. What is curly r? Curly r is del t of r minus r prime. R prime is a fixed vector, and this is changing. So this will be minus of del r prime del t. What is del r prime? R prime is a function of tr. So I write minus del r prime del tr into del tr del t. So, and what is this? This is velocity, minus of v del tr del t. Let us plug this in here. So what we get? We get the minus sign. So minus twice r dot v del tr del t equal to twice c into t minus tr is r. So I can write 2c r. 1c separated out, twice c, and c into t minus tr is currently r. So twice c r into 1 minus del tr del t. So what is the value of del tr del t then? Del tr del t is equal to cr divided by cr minus r dot v. Take a cr common from the denominator, we'll get 1 over 1 minus r cap dot beta. Can you hear me?
Yes, sir.
Okay, so
Yes,
this is the so this is del tr del t, and if you remember the quantity that we calculated in the previous page, the energy radiated or energy or power radiated per. So what is this? Yes, r dot r cap into del t over del tr. This is power radiated per unit area, because time was there, power rate per unit area in the charge on time, right? And then if we want to calculate, so now we want to calculate power radiated per unit solid angle. I hope all of you know what solid angle is, so I'm not going to discuss that solid angle. So dp d omega, what is that? That will be, you see, this is power radiated per unit area, right? And whatever charge, whatever the power energy is radiated by the point charge, will finally, this is the field point, it has to pass through a sphere of radius r. This is curly r. So the surface area of the sphere is 4 pi r square, and So what is the power dp power radiated, total power radiated? This quantity into 4 pi r square. So you do what is r dot r cap del t r into 4 pi r square, and then you divide by the total solid angle 4 pi, because you are calculating power radiated per unit solid angle, and any angular dependence that it may have will be inside this thing sr dot r, and this one you see that depends on r cap dot beta. So this 4 pi gets cancelled. So what we have to calculate, sr dot r, which is already with us, so we have to calculate r square. So what is that? R square, this is equal to r square sr dot r cap, and you see we have del tr, but what we calculated is del t, so it will be inverse of that. That means we have to multiply with 1 minus r cap dot beta, because it is del t by del tr. This is del tr over del t, that is 1 minus 1 by 1 over 1 minus r cap beta. So I have just multiplied it. So this is dp d omega, power radiated per unit solid angle, right? This is power radiated per unit solid angle, and we want to calculate this explicitly. That will give us the radiation pattern in different cases. Let us do that. This expression is already with us. What is sr dot r cap? We have already calculated that. So we shall write that and simplify this. Okay, so one thing I must say, that you should assume that the charge which is accelerating, you in this time interval that you have considered, say t1 to t2, that must be very very short, right? So assume the charge to be accelerated for a very short time, during which this velocity vector beta and beta dot are essentially constant in direction and magnitude. Okay, because if you take a long time interval, the charge particle is moving in an arbitrary trajectory, so it can change direction. So beta and beta dot can also change, and then your approximation may not hold. So what is the approximation? You are assuming that the time interval which you are considering to derive the formula is very very short, within which the velocity and the acceleration vector are not changing much in terms of direction or magnitude. Okay, so that r cap, this r cap vector is also changing by a very negligible amount during that time interval, right? So that you should remember. So we are deriving the entire expression under this approximation. So the approximations are very important when you derive a formula. You should remember, when does it hold? It's not an arbitrary thing that wherever you want you can apply it. So the time interval is very short, within which you are calculating this. So we are calculating dp d omega, the power radiated per unit solid angle, dp over d omega. And now we already wrote the formula. Let me write down once again, r square, and then is r dot r cap, and 1 minus r cap dot beta, right? And this quantity we have already calculated, so I'm just putting it here. So I'm just value r square, and then this quantity which we calculated in some earlier page, 4 pi epsilon 0 q square by 4 pi c 1 over r square, and then we have a mod of r cap cross r cap minus beta cross beta dot square, and then in the denominator we had 1 minus r cap dot beta whole to the power 6, but you see there is a 1 minus r cap dot beta here. So 1 the power will be reduced by 1, so this will be 1 minus r cap dot beta to the power 5. This was to the power 6, and so I'm just not writing this term once again because there is not much space here. So you just read this power is reduced by 1. This was earlier 1 minus r cap dot beta to the power cube square, that is 6. Okay. Okay, so what can we do? Is there any cancellation? Yeah, r square will cancel out. What else? I think I can write down it as it is, 4 pi epsilon 0 q square by 4 pi c, and then we have r cap cross r cap minus beta cross beta dot square divided by 1 minus r cap dot beta whole to the power 5. So this is the general expression for power radiated per unit third angle. Now see, we earlier, when we simplified the Leonard formula, we considered two extreme cases: when the velocity and acceleration are parallel, the other was when velocity and acceleration are perpendicular, right? So in case of collinear velocity, so let us take the first case, case 1, collinear velocity and acceleration. That is, okay, I'm not writing that, beta parallel to beta dot. So as soon as you take beta parallel to beta dot, of course, this will give us beta cross beta dot 0. When they're parallel, there is no angle between them. So sine theta will be, 0. And so if I take this dp d omega in this case, collinear case, so dp d omega will be 1 over 4 pi epsilon 0 q square by 4 pi c, and you see r cap r cross beta dot minus r cap cross beta dot. So beta, since beta cross beta dot, first you take cross product of between these two and then take a cross product with this one. If you remember the order from which these terms arise from the original expression, you will see that these two terms must be, operated first. So you take a cross product between this and then this a third one, and then you take a cross product with the first one. So here I have not put any third bracket here, but anyway, that is implied. And now you see the second term, beta cross beta dot, that will be 0. So only the first, this term remains. So we shall write this to be r cap cross r cap, and be careful, don't write r cap cross r cap is equal to 0, because a cross b cross c, if you change the order of your cross product, the result will be different. R cap cross beta dot, right? This one square divided by 1 minus r cap dot beta whole to the power 5. So this is power radiated per unit solid angle. Now this is the simple expression for a cross b cross c, right? So let us simplify this further. So what will be that? 1 over 4 pi epsilon 0 q square by 4 pi c. Okay, a cross c, b a dot c minus c is beta dot a dot b r cap dot r cap square divided by 1 minus r cap dot beta whole to the power 5. R cap dot r is of course 1, and r cap, this is also okay. Now let us take a square of that, square of a minus b square. So what will be that? Is equal to 1 over 4 pi epsilon 0 q square by 4 pi c, and I'm squaring that numerator. So that will give us r cap dot beta square, beta dot square, because that will give again r cap dot r cap, which is 1. If I square this square into r cap dot r cap, which is 1, plus this one is already 1, so this will be plus beta dot square, and then minus 2ab. 2ab is 2, we have an r cap dot beta already there, and another r cap dot beta will appear here. R cap dot r cap is 1, so twice r cap dot beta dot square divided by 1 minus r cap dot beta whole to the power 5. You see these two terms are same other than this coefficient. So what is there in the numerator? Beta dot square minus r cap dot beta dot square, because this is minus 2, this is plus 1. So beta dot square minus r cap dot beta dot square is the will be in the numerator. So let us go to the next page. So dp d omega in this case, dp d omega in this case. So I'm coming, okay, let me just write down the same expression once again. 4 pi epsilon 0 q square by 4 pi c বিয়োগটা করে দেওয়া যাক, আবার লেখার কোনো মানে হয় না। So it will be beta dot square minus, একটা -2 ছিল, একটা +1 ছিল, r cap dot beta dot square divided by 1 minus r cap dot beta, but not beta dot, I think, yeah, okay, beta to the power 5. So if I take, you see the angle between acceleration and the radius vector is already decided. We have denoted it to be theta. The angle between the acceleration vector, I already told you, acceleration vector a or beta dot and the radius vector r cap is theta, right? So this will be dot product, so cos square theta. So dp d omega will be 1 by 4 pi epsilon 0 q square by 4 pi c, and then if I take a beta dot square common after taking the dot product, that will give us beta dot square into 1 minus cos square theta divided by 1 minus beta cos theta whole to the power 5, right? And beta dot square is what? A square, acceleration square by c square. So this will give us equal to 1 over 4 pi epsilon 0 q square divided by 4 pi c cube and an a square here, and 1 minus cos square theta is sin square theta. Sin square theta divided by 1 minus beta cos theta whole to the power 5. And remember that in this case, I mean, if I take the collinear case, in this case, suppose this is okay, I mean, you can draw the picture as you want. So here I am drawing the acceleration vector here, beta and beta dot, they are parallel, right, along the same direction, and this is suppose the radius vector r cap. So angle between them is theta, right? And we want to draw the radiation pattern. So what will be the directional dependence of the radiation coming out of the accelerated point charge? You can clearly see this dp d omega, power radiated per unit solid angle, which is nothing but the pointing vector multiplied by the area, so and then divided by the solid angle. So that is a physical thing. So see, the angular dependence is basically encoded here, right? So you can think how it should look like. Of course, you should verify that whether this gives me gives me back the Larmor formula, well-known Larmor formula. You can check that. If you want to check it, you can easily check this one, because what is the Larmor formula? Larmor formula is valid for beta is much less than. When beta is much less than 1, then what will be dp d omega? Dp d omega will be how much? You see, this beta is very small, much less than 1, right? So this will be small. So this will be simply 1 by 4 pi epsilon 0 q square a square by 4 pi c cube and then sin square theta. If you remember the Larmor formula, you get exactly this, sin square theta by r square. But why there was r square? Because it was not power radiated per unit solid angle, rather it was just the power per unit area, right? So because here we have multiplied by the area as well, so this r square has got cancelled, right? It is exactly the Larmor formula, not the, I mean, the same non-relativistic case. Larmor formula have to be obtained by integrating this. So this is the pointing vector that we obtained for the non-relativistic case. So in that case, we had sin square theta by r square. You should understand what is the difference between this pointing vector and dp d omega, because here we have multiplied with the area, so r square got cancelled. Otherwise, if you write down this in terms of pointing vector, there will be r square here. This is exactly the Larmor formula, I mean this non-relativistic case. So we can obtain the non-relativistic case from the relativistic case, but of course here the velocity and acceleration are parallel, right? That is fine. In any case, you should get back the non-relativistic case when you apply this beta is much less than 1. Okay, and now we want to understand the pattern. How should the radiation pattern look like? How do you get any idea? I think to get that, you should actually take a derivative of this function. So let us find out the angle along which maximum power will be radiated by the accelerated point charge. How to do that? You just take a derivative of this function d theta of this whole function sine square theta divided by 1 minus beta cos theta whole to the power 5 equal to 0. If you do this, you will get what is theta max, the direction along which the maximum power will be emitted. So let us take this simple derivative. So we are going to calculate this d theta of sine square theta divided by 1 minus beta cos theta whole to the power 5 equal to 0. Right. That is the condition. I mean, because this is what this is the theta dependence of the power emitted. I mean, dp d omega, power per unit solid angle, and this is the we are taking theta derivative of that because we want to find out the angle along which that power will be maximum, right? So this equation should give us the maximum angle. Sorry, not the maximum. The angle along which maximum power will be emitted. It's not the maximum angle. Sorry. Okay. So let us take a derivative. So twice sine theta cos theta. So I am taking derivative of sine theta first, and 1 minus beta cos theta whole to the power 5. And then second, there will be minus 5 sine square theta will be as it is. Here it will be 1 minus beta cos theta to the power 6, and then we have 1 is 0, take a derivative, cos theta becomes sine theta, but cos theta will become minus sine theta. So minus minus plus, so this will be into beta sine theta equal to 0. Let's simplify it. So this will be twice sine theta cos theta. There is 1 minus beta cos theta to the power 5, 1 minus beta cos to 6. So you can throw away this 1 minus beta cos theta to the power 5. You can take that common and throw away. So what we are left with 2 sine theta cos theta into 1 minus beta cos theta minus 5 beta sine cube theta equal to 0. And then just take this common, twice cos theta will be 1 minus beta cos theta minus 5 beta sine square theta. One sine theta is taken sine theta, sine cube theta. So I have taken sine theta and thrown it away, sine equal to 0. That will give us twice cos theta minus twice beta cos square theta minus 5 beta, and sine square theta I'm writing as 1 minus cos square theta, so that I want to write all of them in terms of cos theta. So that gives us thrice beta, because 5 beta minus 5 minus plus 5 beta cos square theta minus twice beta cos square theta. That gives us thrice beta cos square theta plus twice cos theta, 2 cos theta, and minus 5 beta equal to 0. This is a quadratic equation in cos theta, and you can easily write down the solution of it. So cos theta should be minus b plus minus root over of b square minus 4ac. What is b, what is a, you know all of them. This is 3 beta coefficients 2, and this minus 5, this is the entire thing c. So you just put them a b c minus b plus minus root over of b square plus 4ac 60 beta square by 2a. A is 3 beta, so 2 into 3 beta is 6 beta, and then you simplify this, take this common 1 by, this will give us 1 over 3 beta into square root of, because if I take 4 outside, that will give us 4 outside means this will become 15, and when I take 4 outside, that will give us a 2, right? Square root is there, so 2, and that will cancel out. That's why 3 beta, this will 1 plus 15 beta square, and then minus 1. So theta max can be written as cos inverse this 1 over 3 beta and then square root of 1 plus 15 beta square minus 1. So this is the angle along which maximum power will be emitted. Now remember the angular dependence. This is the angular dependence, sine square theta into 1 minus beta cos theta to the power 5. So dp d omega was something multiplied by this. Now if I ask you how the radiation pattern should look like, okay, to figure that out, actually you have to plot this function, but even without plotting anything, you can actually figure out by looking at the expression. See, when beta tends to 1, that means it is extremely relativistic. Say point v equal to 0.99999 c. So beta tends to 1, what should be? So suppose I am telling you that a point charge is getting accelerated with a relativistic velocity of say 0.9999 c, and the velocity and acceleration are parallel with each other. How the what would be the direction along which maximum power will be emitted? Now just by looking at this expression you can figure it out. If beta is tends relativistic, beta tends to 1. For a relativistic particle, beta tends to 1. And if beta tends to 1, you can see beta tends to 1, that means it will be around very close to 1. So 15 plus 1 will be 16, square root of that will be 4, 4 minus 1 will be 3, and 3 cancels out. So 1 by beta, and beta tends to 1, so cos inverse 1, what will be theta max?
0 degree.
0 degree, right? 0 degree. Another important thing to remember here, that okay, beta, yeah. And if that is the case, suppose what you told that for this extremely relativistic particle, you have a situation where the maximum power will be radiated along the direction making an angle 0 with the velocity and acceleration. So theta max is 0. Now if theta max is 0, put it here, what do you get? Beta is 1, cos 0, what is that? 1. So 1 into 1 is 1, and 1 minus 1 is 0, so 0 to the power 5. That means it will blow up. It will be near infinity. Of course there is nothing, we cannot talk about infinity. What I'm trying to say, because beta is not exactly 1, it is tending to 1, because beta equal to 1 is not possible, that you know. So what I'm trying to say, that the quantity in the denominator will be extremely small number to the power 5, right? It's nearly 0, so it will blow up. So what will happen? Entire power will be emitted in the forward direction. So let me just draw the picture here. Remember what was the radiation pattern in the Larmor case? Okay, just so what I'm trying to say is that for beta tends to 1, theta max is around 0 degree, right? And what is the angular dependence of the radiation? This dp d omega, that is sine square theta by 1 minus beta cos theta to the power 5. And when beta tends to 1 and theta max tends to 0, this will tends to infinity, right? Okay, so let us think clearly now. So in case of a non-relativistic point charge, what was the radiation pattern? That was quite simple. Okay, suppose the velocity, we have already shown that they are exactly identical as we can have the same formula from the relativistic formula. So this is, suppose the velocity and acceleration are along the same direction. So in case of a non-relativistic point charge, we already know how the radiation pattern should look like, right? It is something like this. This is known to us, right? So this is the case when beta is much less than 1. What happens when beta gradually increases? You see, but you should also remember the three-dimensional pattern, because this is not this kind of picture which I am drawing on the board. It is actually a donut shaped pattern. So it is a cross section. So you have just to visualize it. Okay, how can I help you to visualize donut? I think all of you know what the donut is. You can also, because donut, the thing is that, okay, you can think about it is not exactly like a tire of a, say, wheel of a bus. It's not like that. Because the central part will be thinner and the outer part will be thicker, right? And that is what I want to say. So you can think about something like that in 3 dimension. And when the velocity increases, what will happen? You have already concluded that when the velocity will be extremely high, the entire power will be emitted along the forward direction. See, in this case, it was 90 degree, right? Velocity and acceleration is along this direction. This is r cap. R cap can be along any direction. The maximum power will be emitted along this direction in case of non-relativistic point charge. But when it is extremely relativistic, what you have concluded that the entire radiation will be emitted in the forward direction. That means this cone will be completely confined in the, this will become a cone, because as you increase the velocity, what will happen? Suppose I go to slightly higher velocity, beta equal to say 0.3, slightly increased. So what will happen? This torus, this is not a torus, sorry, this is donut pattern, will bend forward. So this will something look like this, because it is gradually, again, this is not the actual picture. This is actually cone. This is actually a cone. In 3 dimensions, it is actually cone, right? So I'm just drawing the cross section, right? It's a conical because it has all the, because if you consider x, y, and z, all possible direction, it will be like a cone, right? So maximum power is emitted along this direction. This is theta max. This is theta max. And how to calculate theta max? That formula is already there, because theta max, we have already wrote down theta max. What is theta max? Theta max is cos inverse 1 by 3 beta, a square root of 1 plus 15 beta square minus. So if you know the velocity beta, you can calculate along which the maximum power will be emitted. If you increase the velocity from, say, beta equal to 0.3 to beta equal to 0.6, it will bend by a larger angle. So smaller, sorry, this angle will be even smaller. So it will bend, and it will be something like this. And so you see the length will increase, because this will be increased, because I already told you, in case of this theta equal to this beta tends to 1, it will be infinity, right? So in this case, this is theta max. This is also a cone. So this is a cone, but again, in 2 dimensions, it would not look like a cone. And when you go to beta tends to 1, say beta equal to say 0.9, okay, beta equal to 1 is of course infinity, that I cannot draw. When beta equal to, so this is the direction of velocity and acceleration. This is beta dot. In all these pictures, this is beta dot. So in case of beta 0.9, this will be something like this. It is very difficult to draw, because they will be very thin and very long. Okay, maybe 1 kilometer, 2 kilometer, you can go up to, okay, very long distances. So this entire radiation pattern is confined in the forward direction that we have already discussed. The theta max will be around 0. Non-relativistic, it will be 90 degree. In between, somewhere in between this 90 degree and 0 degree, and bent by a different angle, and that will be decided by the value of beta. If you know the value of beta, you can calculate theta max, right? So this is again a cone, which I have drawn here. It's again a cone, but it's a very extended, narrow cone. It will almost look like a single lobe pointing towards the forward direction, that is along the direction of the velocity or the acceleration, right? So this is the case of velocity and acceleration when they are parallel, beta and beta dot. When they are parallel, the radiation pattern look like this. And this formula can be cast in different form. This is an important formula, and whatever I am discussing in this class are actually borrowed from Jackson's book. You can read Jackson's book for a thorough discussion. What I'm talking or discussing is already there in the Jackson's book, so you can consult Jackson's book if you have any doubt, and also clarify it from me as well. So I will write down the expression for theta max, the other alternate expression for theta max, because this is a very important formula which has a lot of useful application. This formula looks a bit ugly because of this kind of square root and then beta and then cos inverse. So let us simplify it a bit further. So what is theta max? Theta max that we have obtained is cos inverse beta square root of 1 plus 15 beta square minus 1. This is theta max. This is the angle along which the maximum power will be emitted when the velocity and acceleration of the accelerated point charge are pointing along the same direction. And we know the relationship between beta and gamma. So what we are going to do, we are basically going to simplify this expression in case of an extremely relativistic point charge, where gamma is very large, beta tends to 1. So in that case, we shall simplify it. So gamma is known. Gamma in terms of beta, we can write this 1 minus beta square. And so I can write 1 minus beta square equal to 1 by gamma square, or beta square equal to 1 minus 1 by gamma square, or beta equal to 1 minus 1 by gamma square to the power half. Now, in case of a relativistic particle, beta tends to 1. If beta tends to 1, gamma is much greater than 1. So in that case, 1 by gamma square, this will be a very small number. So you can write beta equal to, of course, it's not exactly equal to 1 minus 1 by 2 gamma square, right? And of course, beta square can be written as in the same manner. You can write beta square equal to, it is there, beta square is there, and beta is this, right? So we want to simplify this formula. We want to write down this formula in terms of gamma. I mean, essentially they are same, but it will be a bit simpler or more clean. So theta max equal to cos inverse. I should write equal to, not exactly equal to, because we are approximating this. This is a relativistic particle. Beta tends to 1. It is not exactly 1. Beta tends to 1. So that's why I change the sign here. It is almost equal to cos inverse. And then I am just putting the value 1 by 3 beta. What is beta? Beta is already there. This one is beta. This one is beta. And 1 by 3 beta. So this minus will become plus. If I take it on the, this is 1 by 3 is there. And 1 by beta. Again, gamma 1 by 2 gamma square is a small number. Gamma is very large. So I write it 1 plus 1 by 2 gamma square, right? And then I put it these expressions here. So let us do that. 1 plus 15 beta square. What is beta square? This one. So 15 into this. 15 into 15 minus 15 by gamma square. Let us do it together. So 15 plus 1, 16. And if I take if I combine them, so this will be 16 gamma square. This will be 16 gamma square. This will be 16 gamma square minus 15 divided by gamma square to the power half. And of course, there's the minus 1 here, minus 1. Right, this one. Again, let us simplify. Cos inverse 1 by 3, 1 plus 1 by 2 gamma square. If I take a 4 outside, that will give me, I think, now 16. Let us take 16 outside. 16 outside means that will become 4. That will become 4. And what we are left with inside, this will be 1. Gamma square cancel. That will be 1 minus 15 by 16. 15 by 16 gamma square to the power half minus 1. Okay, I'm doing all the steps here. Cos inverse, this will be 1 by 3. Maybe, okay, I'm not skipping any step. 2 gamma square, and then multiply it, I think, yeah, to the power half. So yeah, so what shall I do? We can write it as 4 into 1 minus half of that. So 1 minus 15 by 32 gamma square. Again, it is the same Taylor expansion, gamma square. And the higher order terms are, of course, dropped. Since gamma square is very large, gamma to the power 4 and all that term will be very high. So you don't need to consider them. Minus 1. This one. So if I multiply, now let us combine all this term. This will be 1/3, this 4, multiply 4/3. I'm just multiplying all the term, nothing else. You can check it yourself. 5 by 8 gamma square minus 1 by 3 plus 2 by 3 gamma square minus 5 by 16 gamma to the power 4 minus 1 by 6 gamma square. See, we shall not deal with gamma to the power 4 terms, because gamma square is very large. So 1 by gamma to the power 4 will be extremely small, negligible. So we can drop this in comparison to gamma square. This is 0. Okay. So then you simplify cos inverse. This will give you 1 minus, you add them, minus 1/3 plus 4/3 equal to 1 minus, you have take this common, 8 gamma square, 3 gamma square, and 6 gamma square. So 24 gamma square in the 24 gamma square. I'm just adding them up. And then 15 minus 16 plus 4. Right? So this will give you cos inverse. How much? 1 minus with that 3. 15, 4, 19 minus 16 is 3. 3 by 24. So 1 by 8. 1 by 8 gamma square. So this is dp d omega. So theta max. Theta max equal to cos inverse. Let us simplify it again. So theta max that we have calculated, theta max equal to, we got cos inverse 1 minus 1 by 8 gamma square, right? Now if you check what is cos of 1 by 2 gamma, you will see that this is equal to 1 minus 1 by 8 gamma square. So what is the cos series? If you remember, cos of x equal to 1 minus x square by factorial 2, and then all the even terms, right? X to the power 4 by factorial 4 minus dot 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 dot. So of course the other terms are not there. So this is basically cos of 1 by 2 gamma. So theta max equal to cos inverse inside cos of 1 by 2 gamma. So this is basically theta max equal to theta max. Very simple to remember. You don't need to remember all that square root 1 by 3 beta and all that numbers. Very simple formula. So the direction along which the maximum power will be emitted is simply given by 1 by 2 gamma. So if I give you the energy of a particle, suppose I tell you suppose there is an electron which is say of energy, say some 100 keV or say 80 keV. Okay, electron with energy say 80 keV. All that you need to calculate to figure out what is the gamma, because what is energy? Energy is m gamma c square anyway, right? So if you know energy, you can calculate gamma, and if you know gamma, you can calculate the theta max. Very simple formula. So that's why I calculated this one. It is the same formula. If you use the beta, if you calculate beta, for in this case beta will be 0.5, approximately 0.5. You can also put the value of beta in the previous formula to get theta max. They will give the same result. But this one is much more simple and elegant, right? So 1 by 2 gamma. So if you calculate this, theta max will be equal to 38.2 degree, right? So velocity and acceleration of the electron are in the same direction. The electron has an energy of 8 keV, and by electron is 38.2 degree that you calculated numerically, right? And so what is the physical interpretation of this? You see, theta max is of the roughly of the order of 1 by gamma, right? There is two factors there of the order of 1 by gamma. That means what is gamma? Gamma is basically mc square divided by E, total energy. This is the rest mass energy divided by the total energy, right? Total energy. That means, you see, what does it imply? This is rest mass energy, mc square, and this is your gamma m gamma c square or gamma mc square. So that is 1 by gamma. That means as beta tends to 1, right, the angular distribution is tipping forward more and more and increases in magnitude. That we have seen, that is a pattern, that as you increase the velocity, as beta tends to 1, gradually this non-relativistic pattern will bend forward, right? It will go like this, and finally it will be something like this, right, which we have discussed, right? And what it is saying, that along this direction theta max, what is the situation? You see, the rest mass energy of the total energy of the particle and the rest mass energy, the particle is rest mass energy divided by total energy is giving you this factor 1 gamma, which is nothing but the theta max. So this is a physical interpretation. I mean, of course, it is just one way to connect the physical meaning of it. So this theta max is given by the ratio of rest mass energy by total energy. Now there is an elaborate discussion on this topic in Jackson's book. So I'm touching all these points because there are certain things which how much time? Okay. All of you can hear me? Hello?
Yes, sir.
Okay. Okay, so what should we discuss next? So this is again from Jackson's book because this is another way of thinking this about this formula. Let me just discuss this also. So what is the see if I plot dp d omega versus say theta, so what should it look like? Okay, to get an idea of that, you have to actually calculate dp d omega in terms of theta, right? Because what we did earlier is that we calculated theta max in terms of gamma. Let us also calculate dp d omega in terms of gamma, not in terms of beta. Again, it's the same formula. Physically nothing has changed. Only thing is that we are writing this in terms of gamma in order to have a simplistic view. So in the relativistic limit, when beta is tending to 1, relativistic limit, theta is very small. We have seen the theta max is around 0, not exactly 0. That you should remember, right? Theta. So in that case, theta is very, very small. Sine theta will be of the order of theta, and cos theta can be written as 1 minus theta square by 2 plus blah blah blah. You don't need to write that. So if I write down dp d omega in this limit, 1 by 4 pi epsilon 0 q square a square by 4 pi c cube, and then if you put this sine square theta divided by 1 minus beta cos theta to the power 5. So sine square theta means theta square, and 1 minus beta cos theta. So I'm multiplying that 1 minus beta cos theta minus beta. So we can become 1 minus beta, and minus minus becomes plus beta theta square by 2 to the power 5. Okay, just algebraic simplification, nothing more. 1 by 4 pi epsilon 0 q square a square by 4 pi c cube. There is a 2 here, so let us take that 2 outside. 2 to the power 5 means 32. So 32 theta square divided by, this will be 2 into 1 minus beta plus beta theta square to the power 5. Now let us put beta in terms of gamma. If you remember, we wrote earlier that beta, what is the relationship between beta and gamma, right? So I'm going to put that beta, because we calculated that in the previous page. Beta is what? Beta was equal to 1 minus 1 by 2 gamma square, if you remember from the previous discussion. So I'm not rewriting them once again. This was beta, so I just put that here. So that will give us 1 over 4 pi epsilon 0 q square a square by 4 pi c cube, then 32 theta square. Let us do the calculation. It will be 2 into 1 by 2 gamma square. This is 1 minus beta will be 1 by 2 gamma square plus beta is 1 minus 1 by 2 gamma square into theta square to the power 5. And if you then simplify this further, we will get 1 over 4 pi epsilon 0 q square a square by 4 pi c cube, and then 32 theta square. See, gamma square is in the denominator, and there is a power to the power 5. So if I take that outside and gamma to the power 10, gamma square to the power 5, that will be gamma to the power 10. Theta square times gamma to the power 10 divided by, and then you 2 will get cancelled. So if you simplify this and drop all the higher order terms, you will get 1 plus gamma square theta square to the power 5. Yes, I can also break down this because this is theta square and gamma to the power 10. Let us write it this way. Okay, I write this to be, say, gamma to the power gamma square and gamma to the power 8. So that gives us gamma to the power 10. The purpose was basically gamma, write down everything in terms of gamma theta. So gamma square, let us write down to theta square here, theta square, right? So gamma to the power 10, I have written as gamma to the power 8 and gamma square. That is gamma to the power 10 only. So the function, you see, gamma square theta square divided by 1 plus gamma square theta square to the power 5. This is the function. So if I plot gamma theta along this direction, how should it look like? Of course, you know along which the maximum power is emitted. If you remember, what was theta max? Theta max was equal to 1 over 2 gamma. That means the maximum power, this maximum will appear. So gamma theta equal to around half, right? So this is gamma theta. So this will go like this and then reach a maxima and then again gradually go down. So this is the value gamma theta equal to half. This is gamma theta equal to half, where the maximum will appear. This is square function square. So this will go like this, and then we have a gamma theta, and this will be symmetric on the both sides. So because see, even though there is a to the power 5 here, gamma to, but this is square, gamma theta square, right? So we are plotting it as a function of gamma theta. So there are two maxima on two sides. This will also appear at half, minus half, plus half, because square, so square makes it same. Maximum power will be emitted at this location, gamma theta equal to half. Again, I mean, what is the purpose of doing this? This is all to, I mean, so what we did earlier, we wrote down dp d omega and the theta max in terms of beta first, and in this last two calculation, what I did is basically I wrote theta max in terms of gamma and I wrote dp d omega in terms of gamma. That's the difference. Nothing new. Okay. So I would show that to get back the same Leonard formula from this derivation as well. If not, then there must be some discrepancy. So by showing that, we can prove that both the approach, I mean the approach that took class of the formula by choosing and showing that formula uses to the Larmor formula in the non-relativistic limit. So let us do that. We shall show that this expression and that expression will match. Okay, how to do that? To do that, because when remember, so in the case, so what was the Larmor formula? Let me just write it once again in order to prove it. Okay, first I write down the Larmor formula. Sorry, Leonard formula. So Leonard formula was P total was 1 over 4 pi epsilon 0 twice q square gamma to the power 6 by 3c, and then we had beta dot square minus beta cross beta dot square. And right now we are discussing the collinear case where velocity and acceleration are parallel. So when beta parallel to beta dot, the power radiated by the point charge is equal to, this will be 0, so 1 over 4 pi epsilon 0, yes, and then twice q square a square, beta dot is a square by c square by 3c cube into gamma to the power 6. So this was the Leonard formula in the collinear case, and we want to see if we can get back the same result from the current derivation. So in the current derivation, we have obtained the expression for power radiated per unit solid angle from the Poynting vector, which was again derived from the original expression of electric field of the general case, that is where the charge particle is accelerating with an arbitrary velocity. So let us calculate. So this is the power radiated. So you want to calculate the power radiated from the expression of dp d omega. So power radiated P, how do I get that? By integrating over all solid angle dp d omega d omega. This is known to us. What is that? This is some factor there. Let us write down that factor. So P equal to, what is that factor? 1 over 4 pi epsilon 0 q square a square divided by 4 pi c cube. This was the factor before this theta terms. And then we have this sine square theta divided by 1 minus beta cos theta to the power 5, which is dp d omega, the theta dependence of dp d omega. That has to be integrated over the entire solid angle, right? This is solid angle, right? So d omega, what is that? Sine theta d phi is a solid angle. So what is dp d omega? This multiplied by sine square theta divided by 1 minus beta cos theta to the power 5. Theta goes from 0 to pi, phi goes from 0 to 2 pi. And d omega, the solid angle, is sine theta d phi, right? The solid angle. Remember, when I write area, r square sine theta d phi, that's the element of area. But this is a solid angle, right? Sine theta d phi. Okay, so let us do this integral and see whether it gives us the same expression or not. What happens? Okay, so let us simplify this. This will be equal to 1 over 4 pi epsilon 0 q square a square 4 pi c q. There is no phi term other than this. There are no phi dependent terms. So d phi will be integrated simply as 2 pi. So we just have to carry out the theta integral, which goes from 0 to pi, and then sine square theta and sine theta, that gives us sine cube theta divided by 1 minus beta cos theta to the power 5 d theta. So we just have to carry out this integral, right? So let us do this integral first. So sine cube theta divided by 1 minus beta cos theta to the power 5 d theta, 0 to pi. So I will just follow a simple method of substitution where 1 minus beta cos theta, let us put 1 minus beta cos theta equal to x. So cos theta derivatives minus sine theta, so sine theta d theta equal to dx by beta, right? And what is cos theta? Cos theta will be 1 minus x, 1 minus x by beta. So what is there? Cos theta, we got cos theta. There is sine cube theta. Okay, so let us write down sine. What is sine square theta? Because we shall take one sine theta outside. Sine theta d theta will be this dx by beta. So what is sine square theta? If you calculate sine square theta, that will be 1 minus cos square theta. So simply 1 minus x square divided by beta square. Just simply add them up. 1 minus x square by beta square. That will give you equal to beta square plus 2x minus x square minus 1 divided by beta square. So let us substitute this here in order to simplify this further. What we do, we write sine cube theta is sine square theta and sine theta d theta. You see, sine theta d theta is dx by beta. Sine square theta, we already obtained this expression, right? This is sine square theta. And you see 1 minus beta cos theta, we have already assumed it to be x. So let us put all of them here. Okay, so 0 to pi sine cube theta divided by 1 minus beta cos theta whole to the power 5 d theta. I am just substituting the value. Sine cube theta is broken into sine square theta into sine theta d theta. this has been assumed to be x. 1 minus beta cos theta is x. And we have already obtained the value of sine square theta, and sine theta d theta is dx by beta. So if I put them, this will become 1 by, of course I have to change the limit. So remember what was x, 1 minus beta cos theta was equal to x. So the limit, so cos 0 1, so limit will be 1 minus beta, and it's pi, so this will be 1 plus beta, and the d theta is dx by beta, and this will throw away another 1 by beta square here, so 1 by beta cube, and then we have beta square plus 2x minus x square minus 1 divided by x cube into ds. Now this is a very straightforward integral. You see there are only power of x square, x cube, and so on. So all that you need is just carry out this integral and put the limits. Lower limit is 1 minus beta, upper limit is 1 plus beta. Right, so you just have to do that. Again, it will take this entire 1 page. So I am not doing that. You can just simplify this and put the limit, which will give you equal to 4 over 3 into 1 minus beta square whole cube, right? So I would suggest you to check this because I am writing this value just to avoid because this is just will take some time. It's nothing complicated, or I think no discussion is needed on this particular thing, because just have to put the limit. So this one is the integral. Now let us put this value in the expression for p. What was p? dp d omega d omega, and we already got that equal to 1 over 4 pi epsilon 0 q square a square by 4 pi c cube. There will be 2 pi terms coming from the pi integral, and the theta integral gives us this. What is that? 4 by 3 into 1 minus beta square whole cube, right? Now you simplify, 4 will get cancelled, pi will get cancelled, 4 will get cancelled. So you simplify all that. Finally, 1 minus beta square, you know that you can write down in terms 1 by 1 minus beta square is gamma square. So 1 by gamma square to the power cube. So gamma to the power 6 will be on top of that. So that will go to numerator. So you'll get 1 over 4 pi epsilon 0. 2 is there. Twice q square a square by 3c cube into square to the power cube. So that goes on in the numerator, gamma to the power 6. Now remember, this is exactly the expression that we got from Leonard's formula in the collinear case, right? So as I told you in the last class, that both of them actually lead to same. The thing is that in this case you have to, if you want to write down in terms of the Poynting vector or dp d omega, the expression is a bit more lengthy, and you have to integrate all the through all these steps to arrive at the formula. So that's the reason I chose the first option, where we tried to find out a Lorentzian variant to give us back the Larmor formula in the non-relativistic limit. There was no other reason. But again, we have checked this, that both of them actually give us the same result. Okay. So I think I will not go to the second case, because again that will take a lot of time, because the second case is when the velocity and acceleration are perpendicular to each other. So this is the case where the velocity and acceleration were parallel, collinear. So we will discuss that in the next class, not in this class, because otherwise the things will be incomplete and I have to again restart from the beginning. So that's why I'm not starting that discussion. Now if you have some question, we can try to quickly answer some of them. আচ্ছা, আরেকটা ব্যাপার তোমাদেরকে এটা আগে হয়তো আমি বলেছিলাম যে কালকে ক্লাসটাতে যেটা আমাদের ঠিক হয়েছিল 1 জানুয়ারি ক্লাসটা হয়নি, সেটা আগামীকাল নেওয়ার প্ল্যান ছিল, কিন্তু আগামীকাল একটা বোর্ড অফ স্টাডিজ মিটিং আছে। তো তোমরা কি ঠিক করেছো অল্টারনেট ডেটটা? ক্যান ইউ হিয়ার মি?
হ্যাঁ স্যার।
হ্যাঁ, বলছি তোমরা কি কোনো ডেট ঠিক করেছো? কারণ আমি ঠিক করে নিতে পারি, কিন্তু সেটা করছি না এই কারণেই, তোমাদের তো নানা রকম ক্লাস থাকে এই সাবজেক্ট সেই সাবজেক্টের কারণ, তাহলে যাতে ওভারল্যাপ না হয় তাই জন্য একটা ডেট তোমাদের তরফ থেকে এলেই ভালো হয়। কারণ আমাদের টাইম খুব অল্প, হ্যাঁ আমাদেরকে মানে ক্লাসটা এই কারণেই আমি মানে লুজ করতে চাই করা যাবে লাস্ট ক্লাস নষ্ট করেছি সেই সময়, নষ্ট ঠিক নয়, বলবো যে আমরা স্পেন্ড করেছি, রাইট? সো যেটার জন্য আমাদের এই পুরো 100% সিলেবাস শেষ হবে না, আমি চেষ্টা করবো অ্যাটলিস্ট যতটা সম্ভব করা যায়, অ্যাটলিস্ট 90% চেষ্টা করা যাক। তো তোমাদের আরেকটা অল্টারনেট ডেটের কথা বলেছিলাম আমি, তোমরা কি নিজের মধ্যে ডিসকাস করেছো?
ব্যাস
Yes,
ঠিক
no?
হয়নি, আমরা আজকের মধ্যে জানিয়ে দেবো স্যার।
তাহলে আচ্ছা ঠিক আছে, তাহলে একটা কাজ করো, আমাকে হোয়াটসঅ্যাপে জানিয়ে দিও। হ্যাঁ, আর একটা জিনিস যে তোমাদের মোটামুটি ভাবে এই একটা মিটিং ছিল, সেখানে আলোচনা হয়েছে, আমি বলেছি প্রথমে বলেছিল সেকেন্ড উইকে ক্লাস সাসপেন্ড করে দেওয়ার কথা, কিন্তু যেহেতু আমরা অনেকেই বলেছি, মানে আমি বলেছি পার্টিকুলারলি আমার কথা মাথায় রেখে যে ক্লাসটা যাতে থার্ড উইক পর্যন্ত অ্যাটলিস্ট এক্সটেন্ডেড হয়, কারণ তোমাদের পরীক্ষাটা মোস্ট লাইকলি নেক্সট মান্থের গোড়াতে শুরু হবে। এখন পর্যন্ত যা প্ল্যান আছে চেঞ্জ হয়। আমাদের মনে হয় একটা ছুটি আছে, মূলত কবে একটা যেটা ইউথ ডে আছে সেদিন মনে হয় ছুটি আছে, যেটা ন্যাশনাল হলিডে, তো সেখানে ক্লাস হবে না, তাহলে আবার একটা ক্লাস নষ্ট হবে। সেই জন্য আমি 1 জানুয়ারি ক্লাসটা তোমাদের বলছি, একটা অন্য কোনো দিন তোমরা আমাকে শিডিউল করে জানাও। আর তোমাদের নোট আমার লাস্ট 2টা ক্লাসে পেন্ডিং পড়ে গেছে বিকজ অফ ব্যাপার হচ্ছে আমি গুছিয়ে নোট বানানো আমার কোনো বছরই হয় না, আমি আসলে জাস্ট এদিক ওদিক স্ক্রিবল করে রাখি, সেগুলো আবার নতুন করে স্ক্রিবল করি। এই বছরই প্রথম তোমাদের যেহেতু এইভাবে পড়াতে হচ্ছে বলে নোট বানাচ্ছি, বাট এনিওয়ে আমি নোটগুলো তোমাদের দিয়ে দেবো, যেগুলো পড়াচ্ছি এখন পুরোটাই জ্যাকসনের বইয়ে আছে, ইন্টারমিডিয়েট স্টেপগুলো হয়তো করা নেই, তো আমি চেষ্টা করবো কয়েকদিনের মধ্যে নোটগুলো দিয়ে দেওয়া যেগুলো পড়ানো হয়েছে।
ওকে স্যার।
ঠিক আছে, ওকে ওকে।